All right, so we're going to talk about some models of the atom today, and we're going to get to some other topics. So, Thomson's model of the atom is the first one we're going to talk about. And he found that electrons were small and negative. So he proposed a model where the rest of the atom was positive, so that's kind of like that positive, and then there were just like small little negative things over here. So he proposed a model of uniform distribution of positive charge in which electrons are embedded, like raisins in plum pudding, which I think was like some kind of baked good around when Thomson lived. Your chemistry teacher might have told you to think of this raisins in plum pudding more like chocolate chips in a cookie. They're just kind of floating around embedded in the rest of the things. Now, if that had been true, when Rutherford shot a bunch of positive charges at some atoms, they should have all bounced off of that cookie part, that positive part that the electrons were embedded into. So he shot positive charges at atoms, and only a small percentage were deflected. So that must mean that the positive charge that they deflected off of wasn't very big. So he figured that the electrons were orbiting, the nucleus, and they would accelerate due to the direction of their motion towards the center. So this didn't really explain why they didn't go towards the center. So according to his model and understandings of classical physics, the atom should have collapsed. So then Bohr came along and he developed his model of the atom, which was the first true modern physics example of an atom. It's long ago, but it's considered modern physics because it's not classical. All based on this idea that electrons exist in specific energy levels. So a stationary state just means that all the electrons are in one level, they're not going between levels. And these levels, for hydrogen, they're n equals 1, n equals 2, n equals 3, all the way up to n equals infinity. And that's most of what is talked about. You also can talk about Mercury's energy levels. So those are A through J. And these are on your reference tables on page 3. You can see both of these have a ground state, which is the lowest energy level. You'll notice that it's the highest number in magnitude, so that's 13.6, and then that's negative 3.4, and that's negative 10.8, and that's negative 5.7. That's a negative number. So the bigger the negative is, the smaller the energy actually is. Ground state is your lowest energy level. And for hydrogen, that's n equals 1, and for mercury, that's n equals a. An excited state just means that electrons have jumped to higher energy levels. So it'll jump to a higher energy level because it's going to actually absorb electromagnetic energy, or light. And then when it falls back down, it's going to emit that back out. So your emitted energy happens when an electron falls to a lower energy level. It's going to emit a photon where the energy of the photon is just equal to the difference in the energy of those levels. So let's do an example. Let's say we have energy going from the n equals 4 to the n equals 2 of hydrogen. Well, the n equals 4 state is going to have an energy of negative 0.85. You can see that by following this little guy here over to this little guy. So these little dashes are weird. You can try to follow. That's n equals 1, so that's n equals 1, n equals 2, 2, 3, 3. So 4 is that negative 0.85. And those energies are in electron volts. I want to write that as electron volts, and then n equals 2. Well, that was negative 3.4. So n equals 2 gives me a final energy of 3.4 electron volts. Now the equation is written kind of weirdly because of that negative, but we're just going to find the energy of the photon by using EI minus EF, and then I'm going to plug in numbers. That's negative 0.85 electron volts minus the negative 3.4 electron volts. And if I plug that into my calculator, I get 2.55 electron volts as the energy of that emitted photon. And that's what happens if an electron falls from a higher energy to a lower energy. So n equals 4 to n equals 2. But how does it go the opposite direction? It goes the opposite direction because it absorbs energy. So absorbed energy from photons makes the electrons go to higher energy levels. And if the electron's energy goes above 0, so let's say it starts at that negative 3.4 n equals 2, and it absorbs more than 3.4 electron volts of energy, what happens? Well, the electron's energy goes above 0, and it leaves the atom. And the atom becomes ionized. And I know I'm running out of room here, so I'm going to have to sneak up here. But that if it has leftover energy, that leftover energy becomes kinetic energy of that electron. So the more energy it has left over, the faster it's going to move when it's done. Now, in order to make sense of atomic spectra, I want you to consider an example. Let's consider that the electron goes from n equals 4 to n equals 1. I want to know how many different ways can it get there? So we got n equals 4, n equals 3, n equals 2, and n equals 1. Well, the electron could start here and just go all the way down, and we could just have one photon emitted there. But it doesn't necessarily have to. It could also go from n equals 4 down to n equals 3, then down to n equals 2. It could stop at every level. Or it could stop at some and not others. You could go from n equals 4 to n equals 3 and then go all the way down. Or it could go from n equals 4 all the way down to 2, but then stop at 2 and then go down to 1. Now, each of those lines is going to emit an electromagnetic energy of a specific energy. And each of those amounts of energy corresponds to a different frequency of light that we see, because the energy of an electromagnetic energy is equal to h times f, where h is a frequency. So we might see, if we were to look across all frequencies using some devices that allow us to do this, we would see certain spectral lines, right? We would see a spectral line for each different frequency or energy that we see. Well, we have the one energy, right? From n equals 4 to n equals 1. We have an energy from n equals 2 to n equals 1. We have that one here and here, but that would be one spectral line. And this guy would be a different one. And this one would just be one spectral line. And how many are we missing? We're missing 1 and 2. So because of the 6 different arrows, right, we drew more arrows, but some of them turned out to be the same. We have 6 spectral lines. Thank you. I know that one was a little bit longer. Again, I hope you're enjoying your time without me.